Unseen and unsafe, why ECU cybersecurity needs binary level truth. Object security does precision vulnerability detection for defense and critical infrastructure. It's about us. So a couple of topics that we do: vulnerability analysis of binaries, so that's software, AI, ML systems, 5G, supply chain risks, and we also do some zero trust architecture stuff. So enough about us, and there was obviously the wordy intro that in the bio, so I'll skip that part. Important to motivate here why I'm here today. So there's a pretty large attack surface. Military ground vehicles today are, to a large extent, software-defined systems. So there are circuit boards with firmware in many of the devices in a vehicle. There are many ECUs, so that's electronic control units per platform. And the supply chains, especially in the commercial world, but also in the DoD, are complex and often opaque, right? So that causes real verification gaps. Critical vulnerabilities can go undetected. Yeah, it compromises operational trust if these devices, the vehicles, don't work as intended. And there's a lot of reliance on supplier claims. So a lot of it gets pushed down the chain to the manufacturers, and that's really problematic when you can't verify that yourself very easily as a buyer. So there's gaps here. In short, software and firmware is everywhere, and it really needs to be covered. So there are some examples here: Jeep hack, 0 day. So that's interesting one that you can search online, where it's obviously self-explanatory what happened. And then cars via CAN injection, that's been around many years. People getting onto the CAN bus and doing bad things to cars, stealing cars, etc. So yeah, that's just to motivate that there is a problem, right? So there is a cybersecurity blind spot, and that is that normal ECU and firmware is not inherently designed to be secure, right? So a lot of them are designed from before people were really thinking so much about security. So they're older, and sometimes they're just assumed to be in a secure environment, and sometimes it's just forgotten, right? Or there is no commercial incentive. So ECUs are everywhere though, drivetrain, etc. Each is a potential attack vector. There's often proprietary, old, often unreviewed firmware. Like I mentioned, supply chains are really complex and opaque. Quite often people can't trace all the way down through the supply chain to even where stuff comes from. That's especially when open source software is baked in. And there's really no visibility, or not enough visibility, into which ECUs are secure. So a single compromised ECU can affect mission critical functions like braking, communications, targeting, etc. Those kind of web screenshots that I've shown you on the previous slide, they kind of illustrate that, right? So that's really a problem. Now, I think in addition to having a cybersecurity problem, there's also the second part to it, which is that traditional cybersecurity countermeasures fall short. So they're not useless, but they're not enough, right? So one thing that obviously everywhere in the government supply chain and in automotive and everywhere gets used a lot is software bill of materials, SBOMs. So that's where a software manufacturer just has to provide you a list with all dependencies, right? They're often incomplete, lagging behind current issues. They often don't reflect the actual binaries, but only the metadata of binaries. So for example, if you were to hack a particular version of a binary and then change also the metadata, say the version of that binary, to a version that doesn't have a vulnerability in it, then the SBOM tool will still think it doesn't have it in it, even though you just hacked it and it's in it, right? So it's a nice tool, SBOM, but it's not enough. And then also the military stuff isn't in it. A commercial vendor will not have a database of all of military equipment. Static source code analysis is another one. So that, by its very nature, requires source code, right? So that you often don't have, and misses edge cases. Static binary analysis is one. So it's sort of a pattern matcher over the firmware. A lot of false positives with that, and also it just looks for known stuff. I want to also quickly talk about the CVE, so common vulnerability enumerations. That's standard for vulnerabilities, and the National Vulnerability Database holds those, operated by NIST and a bunch of others. Unfortunately, that database lags months and years behind, so there's a window, especially for embedded systems, of 2 years, for example, before an attack that has been discovered is in fact in that database, right? So that's really a problem. So the real attack surface here is also in the binaries. People often forget that. And I said here, not in systems engineering or compliance docs. Now it can be there too, of course, but I just want to make the point that this is in the actual binaries, that people have to look at that. They need to start look at the actual software, right? 0 days can exist years and years, by the way, undetected and unpatched, right? So it's not just because something's in production for a long time, it's safe. All right, let's talk about binary level insights here. How do we use binary analysis to figure out what's going on with these firmwares on the ECUs? So if you think of binary, it's the ground truth of what really executes, right? It's as close as it gets when you're talking about software to reflecting the actual running. So that's very different from source code, which is a lot more abstracted, right? So deep binary analysis is trustless in the sense that you don't have to trust somebody for an SBOM or something. You get the ground truth. It's independent. It allows independent verification. Numerous approaches. So I'll be talking quickly about symbolic execution. There's taint tracking, there's patch diffing, firmware fuzzing. These are all techniques, interesting technical techniques. I would say symbolic execution is like fuzzing, but without the brute forcing. And what fuzzing does, fuzzing essentially goes through every possible path through a binary and tries with every possible value and tries to see which ones basically cause a buffer overflow, etc. So symbolic execution achieves the same thing with math, essentially. Taint tracking propagates inputs through a binary to see where certain inputs land. So there's a lot of scientific techniques for that. Example here, sort of fictitious example, symbolic execution uncovers logic flaws in a widely deployed ECU that is often missed by SBOM and source tools. So that would be kind of like a use case. So I can uncover 0 days because you're looking at the ground truth of your binary, not some kind of database of NVD or something. It's deeper than pattern matching. So pattern matching is static analysis, no source code required, and can work for legacy and proprietary firmware. So that's important for the military especially, right? Because stuff might be classified or just specific. So with that, related to this binary vulnerability analysis, I'd like to briefly present this SBIR that we're currently doing for, in fact, like as I mentioned, for DEFCON. The TPOCs are here, right? The goals of the project was to build essentially an ECU cybersecurity simulator, enable a repeatable, scalable cybersecurity testing tool without the physical hardware, so without the ECU in hand. The backdrop to that was to speed up secure design and reduce cost and schedule risk, right? That's important because, rehosting binaries for anyone that's in this field is very challenging. So what we figured is that we integrate symbolically executed binary analysis into the digital twin workflow. So it is like a digital twin, but it is not rehosting the entire thing. We tried that, and that's very challenging, right? So what that thing does in the end is it supports analysis for binary level vulnerabilities, and I get to what those would be. There's a link there, M2SIM is basically the link here. So with that, what's the SBIR program? It's essentially a funding program for small business that stimulates tech innovation by small business to meet, in this case, defense needs, right? Second point is, though, to increase private sector commercialization. With that, I want to kind of talk about this commercialization. So we commercialized BinLens, TRL9 fielded product out of this and other SIBRs. And there's a list of cool things that I'm quickly going to go through to explain a little bit what that does. So it's for accurate deep binary vulnerability analysis, as you would have guessed from what I've just described earlier, right? Fully automated tool with high accuracy and minimal false positive. And we can talk afterwards what that means, because it means a lot of things to different people. But compared to something like a static analyzer or a source code tool, it's highly accurate. Uses this symbolic execution that I mentioned. Mainly looks at memory safety vulnerabilities like buffer overflows and things like that. Interestingly, provides the inputs to reproduce vulnerabilities. So you can think of that like a proof, right? So the proof is essentially run this binary with these input conditions and this buffer overflow will occur. Similar to a fuzzer, just faster. Because it's using the actual binary and not some database, it is able to find 0 days potentially. So it's not reliant on this lagging published vulnerability data. Supports things like ECUs, IT and OT based. Can be used, like I think I've mentioned earlier, for unpublished, proprietary, and classified software, right? So we can deploy this thing on-prem. That's a military requirement, of course, so that you can use it for, say, you build your own ECU or something in the military, right? So that's very different from other kind of usually commercial civilian products. Users include like testers, so that's red teams, etc. DevSecOps, that's the developers, and operators, that's 3 user groups. So I do have a quite convoluted picture here, but maybe preferable is if people come to me afterwards, I have a flyer version too, so I don't have to go into detail through it. The short of it is there's a screenshot in the middle, and on the left you can see you basically feed your firmware, your binaries into the tool. It crunches it, potentially on a Kubernetes cluster for scalability, and then provides an output. And that's a report of identified vulnerabilities. There's a lot more to it, but the symbolic execution-based features are on the left in the small bullet list. There's things like stack overflows, heap overflows, user-controlled redirection, double freeze. These are all typical binary vulnerabilities that can break, in the normal case, in crash a binary, or it can reveal information. So that's what we're focused on with this. It's awardable under things like DoD Marketplace, Platform One Marketplace, etc. So that's the commercialization piece. Now, interestingly, quick footnote to this whole presentation here. So why do we still have problems? Why is it not done? The tool's there, the research has been kind of done. Why? So what we found, and this is leading to a different kind of research effort we've done, there's an incentive problem. There's basically no market pressure to really secure ECUs, especially not in the civilian world. Buyers can't really compare cyber resilience between different vendors and their ECUs. So, operators or manufacturers aren't doing better on security because it's not a selling factor, right? There's no metrics, no transparency, etc., and it's always about cheaper. So, here's kind of the thinking guy in the middle. So when you think about it, the asset buyer, so that's somebody buying an ECU and integrating, how do we get this guy to choose more secure devices and software over less secure one, right? And then for the device manufacturer, the question is, well, why do I invest in better device and software security as a selling point, right? So making better security more transparent is kind of the question there. Here's the thing on the side with more money. I mean, that's really what drives manufacturers, right? It's 3 things. We've done a lot of market research there. It's either I sell more product, or I need it because of compliance, or I can avoid a lawsuit this way, right? So how do we get to this? We've done some also SBIR research with NIST on this. That was kind of interesting. So in the short of it was a 6-month SBIR project where initially the proposal idea was to reduce technical barriers, integrate vulnerability management across stakeholders, et cetera, et cetera. Seemed to make sense back then. Well, turned out didn't really. So the first activity we did was market research and realized that assumption wasn't even true, right? We literally talked to over 100 people, and it was interesting that this incentive question came up again and again, right? Like, why would we even do that? So what we did in the end, what we came up with in this project was a public scoring website. There's a proof of concept there at nct.objectsecurity.io, right? That you can actually go to, it's free. It essentially ranks manufacturers based on a published algorithm in terms of how well they're doing in terms of cybersecurity, right? Yeah, so really that sounds great, and I'm sure there's other efforts like this. So the first thing that we had to do here was figure out how do we create trust in this service, especially coming from a small company, right? Nobody trusts it, nobody wants it. So we made everything public. That was one of the things. If the calculations are public, the data is public, full transparency how the scoring is calculated, then people can, for starters, believe it, and secondly, they are able to improve themselves. So NIST, that's the bottom bullet here, the NIST repeatedly mentioned that it should be positive reinforcement, like highlight positive scores and enable improvement versus bashing manufacturers that aren't doing well, right? So that was kind of interesting. I can go into detail there, but not in this talk, so talk to me afterwards about there's 4 things right now that feed into the score. And related to what I described earlier, so binary analysis helps enable transparency also. So, you can see if you find vulnerabilities using binary analysis that isn't in the CVE database yet, that should impact the score, either passing the test or not, right? So yeah, takeaways now. Vehicles are software defined and inherently vulnerable. I think there's really no way beating around the bush there. Traditional methods, that's security methods, give a false sense of security and are not scalable, right? So we talked about SBOM, etc., source code analysis. All good. I'm not trying to bash it, but it's not enough. Binary analysis provides evidence-based assurance on the ground truth of your firmware, not some third-party database or something. We talked a little bit about M2SIM, the SBIR and the Binlens product, and shown that it's possible. The tools are there, the research has been done, but we also need an ecosystem-wide shift, right? So that's something where we all need to work together. I showed you that NCT project. And my call to action is essentially build binary-aware security tools into your workflows. So that's development workflows for the developers and testing workflows for the buyers. Push for transparency in ECU cybersecurity. Don't just take some random report or do nothing or assume it's fine because it's old or whatever. And then lastly, and that's the hardest one, align incentives such that you reward security, right? So that's especially for manufacturers and to encourage manufacturers economically to do better on security. And that really concludes it from my end.
Very good. Thank you. We're just a little bit over our time, so thank you very much.